Hello, welcome back to Solution Equilibria Part 7. We're going to look at a couple more titration calculations and figure out a few things with that. So if I'm looking at the titration of two monoprotic acids, both of them are 0.1 molar, and I titrate them with a 0.1 molar NaOH, so I got a 1-to-1 situation. I find that the first acid gives me an 8.8 pH, and the second acid gives me a 7.9. So I name those acid, which is what we put the H there in front, HX and HY to sort of separate them. So what do we know? Well, both of these are greater than 7. So we know that they're both weak acids. And if we're comparing them to each other, we can see that this one is actually the stronger of the two weak acids because it gives a number closer to 7. Remember, strong acids would give 7. So if we're at 7.9, you know, we're stronger definitely than this one that winds up at 8.8. And so another question also arises is which indicators might we use? So for 8.8 HX, you just got to go over here and take a look and see which one lines up. Let's see, that one would be an 8.8, so thymol blue would work and phenolphthalein would work. We get 8.8 in there. So it looks like those are the only two for that one. For the 7.9er, yeah, you'd probably be able to get away with both of these, and you might even be able to get away with that one. So thymol blue, you could actually use any of the three for the 7.9. It's kind of this one probably be the best because it actually sort of touches that line, but this would sort of give you the lower end. This would give you the upper end of it, so that'd be good. All right, let's move on to another problem right here. So let's say that we had a 25 milliliter solution of a monobasic 0.1 molar weak base, and we titrate it with a strong acid of the same molarity. So the question is the equivalence point. So what do we know? We've got a weak base, and we're titrating it with a strong acid. So the equivalence point we know is going to be less than 7. So we know for sure it's going to be less than 7. So that's one thing that we know right off the bat. Some other questions, how many moles of the strong acid are going to be used for equivalence point? Well, at equivalence point, the moles of the strong acid are going to match up with the moles of the weak base. And so what do we have? Well, we're going to have, let me see, I can erase that right there. We're going to have 25 milliliters of that weak base at 0.1 molar. So let's just do this at 0.1 molar. So actually, I messed that up. So 25 milliliters, it should be 0.025 because we've got to convert it to liters. No longer milliliters. 0.025 liters times the new molarity, which is, or the molarity it has, which is 0.1 molar, and that is going to equal 0.0025 moles. So we have exactly 0.0025 moles of this weak base, and so that's the exact amount of moles it's going to take of the acid in order to get to equivalence point. So one of the things that I did was I went ahead and I sort of kind of wrote out a scenario. So let's say B is our weak base, and a good example of that would be NH3 because that's a weak base like that. And so we'd add HCl. We add the strong acid. So titrate with the strong acid. What's that going to do? Well, it's going to take and it's going to this base is going to join up with this hydrogen from here. So it's every single one of these is going to join up with one of these and create this compound right here. So we can see that this compound right here, NH4, if it's a weak base, it's going to create then essentially a weak acid. And so what's going to happen with that is that that is going to then potentially go back the other way and release some of these hydrogens in solution. And so then the pH, to actually find the pH of this, you're going to need to know two things. You're going to need to know the Ka of that weak acid, and you're also going to know the initial concentration of that weak acid. So you could use this equation right here, plug in the Ka, figure out the concentration of the hydrogen ions that you would have if you know the initial concentration of that. So you would need those two factors. You would need the Ka and the initial concentration. But if you had those, you could actually find the pH at the equivalence point. And I've got one more, and I decided to do a fun little drawing for you because I'm really actually quite good at drawing. As you can see, here's my titration setup. And so the question is, if this is just kind of a typical titration, we have perchloric acid, which is a strong acid. We have potassium hydroxide, which is a strong base. We're going to titrate these together. And so here's the question. What is the pH if I had 30 milliliters of the acid titrated into the base? So it's equal volume, right? So I'd have 30 milliliters of this going into 30 milliliters of this. And that's fine, except for the fact that the molarities are not exactly the same. So I have 0.150 molar for the acid and 0.200 molar for the base. So what we need to do is actually figure this out mole for mole. So how we do that? Well, it's pretty simple. For the base, we got 0.200 molar, and we're going to multiply that times the volume we have for the base, which is 30 milliliters, so 0.030 liters, and that is going to give us an amount of moles of 0.006 moles. Now, if you don't like that sort of shortcut way, you could actually just set up a proportion. So this is 0.200 moles in 1 liter. That's what molarity is, and we want to know how many moles in 30 milliliters. So this is a proportion. That's why we use liters up here. So you cross multiply and divide, but to save time, if you know how to do it, you can just multiply these out. So you get 0.006 moles of the base. So let's put the OH right there. And then what do we have of the acid? Well, we have 0.150 times 0.030 liters of the acid is going to equal 0.0045 moles of the acid. Okay, so remember, when you're titrating strong acids and bases, they just cancel each other out. So clearly here we're going to have a surplus, and that's one thing you always want to keep in mind. Which one ends up with some left over and which one doesn't, and then that's going to lead you to being able to solve for your pH. So what we find is that we have 0.006 moles of this, 0.005 moles of this, and so what do we end up with? Well, we end up with 0.0015 moles in excess, because these will cancel each other out and whatever's left over. So the 0.006, you just subtract that from there, and you find that you have 0.0015 moles excess hydroxide in this case, because this has got the higher molarity. And so then to actually solve for the molarity of it, you're going to divide it by its total amount of volume. So we had 30, we added 30, so my total amount of volume is 60 milliliters. And so that's going to actually give me a new molarity. So that makes my new molarity 0.025 molar. And if I want to find pH of that, actually I'd be finding pOH because this is a hydroxide ion concentration. I take the negative log of that. The negative log of that is going to give me 1.60 for my pOH. If I subtract that from 14, I can find that the pH equals 12.4. So any titration thing, you just really just have to analyze what am I putting in there, what is canceling out, what's left over. Whatever's left over is going to determine your pH. All right.